Okay, so today what we're going to talk about is the logarithm. We're going to just stick with some basic stuff. We're going to learn how to switch forms between exponential form and logarithmic form, back and forth. And then we're going to graph logarithms. So that's what we're going to look at today. So hopefully by the time you leave, you can do all those things. So here's like a mathematical definition of logarithms. Log base a equals x if and only if a to the x equals b. Okay, let's talk about what that means in plain old English. Okay, if we have a log to a base, a logarithm solves for the exponent. So it's always going to equal the exponent. So the base goes here, and I call it the answer part, goes here. And it equals the exponent. So what would that look like in exponential form? Well, if I switch forms, it would be the base raised to the exponent equals the answer. So this is just a different form, and this is the form we need to be able to solve for the exponent. See, in log form, it equals the exponent. So if we were to do if we were writing this on paper, the log, the answer, and the exponent all go on the same line. My answer part's a little high. Let's see if I can shift that down a little bit. Yeah, there we go. And the base is slightly lower. It's a subscript. So does that form make sense? Log, base, answer equals exponent.
So log and answer are on the same level?
Yes. Log, answer, and exponent are all on the same level, and the base is a little lower. Okay, and then when we have natural logs. Natural logs are just like using e. When we talked about e is the natural number, well, when we take a logarithm of base e, then we have a natural log. So this is natural log of b equals x if and only if e to the x equals b. So what does this mean? Natural log means log base e. It's kind of shorthand for log base e. So we won't ever write log base e. Instead of writing log base e, we'll write natural log.
Is that e a subscript?
It is. Now, I say natural log, and it's written ln. In English, we would put our adjectives in front, a natural logarithm. But in other languages, the adjectives go after. So that's where this comes from. That's why it's log natural. I think it is Latin. I'll have to double check that. But I think that's why it's in this form, ln. Okay, first thing we're going to do is just practice some very simple conversions. All these are in exponential form, aren't they? We have a base raised to an exponent equals an answer. A base raised to an exponent equals an answer. A base to an exponent equals an answer. So we're going to switch from exponential form to logarithmic form. So it becomes log, what is your base? 2. What is the answer part? 8. And a logarithm always solves for the exponent. So in number 1, what's the exponent? 3. Okay. Number 2, let's switch forms. This becomes log, what is your base? E. Of the answer, what's the answer? 4. And it always solves for the exponent. Well, log base e is best written as natural log. We won't ever write log base e. We'll always write that as natural log. So this just becomes the natural log of 4 equals x.
When you plug in your calculator, you plug in log base e?
There is an actual natural log button on the calculator. So number 3, you guys tell me. Log base 2 of 1/8 equals -3. Beautiful. Okay, now this is base 10. Our number system is based on base 10, isn't it? To the 0 is our 1 spot, 10 to the first is our tens, 10 squared, 10 to the second is our hundreds, 10 to the third is our thousands. 10 is special, and when we write it as a log, it can be written like this, log base 10 of 1,000 equals x. But base 10 is very common, and it is called the common log. You actually don't have to write base 10. If there is no base written, it is assumed to be base 10. That is the common log. Okay, let's add one more down here. Let's do e to the third equals y. What would that be if I switch forms? ln of y equals 3. Okay. All right. Now let's go the other way. If you're given logarithmic form, can you rewrite it in exponential form? All right, look at number 5. What is your base in number 5? 3. What is your exponent? 4.
81.
Good. That's not 81. There we go. Okay, you try 6 and 7. Okay, did you get x to the third equals 216? Did you get 8 to the negative third equals 1 over 512? Okay, now let's look at this one. If I'm switching forms, what is the base when it's natural log? E. So it becomes e to the x equals 52. All right, any questions?
No.
Okay. So now let's see what we can connect between exponentials and logs. Since logs undo exponents, if we think of them as functions, we can think of them as what? Inverses. So if we graph them, when we graph inverses, they are symmetric over what line? Yes, that one. What is that line?
Y equals X.
Yes, it is.
Attaboy, Harker.
Yes, it is.
It's not Harker, Henry. You gotta have that.
So when we find points on a logarithmic graph, what would we need to do to the points on the exponential graph if they're inverses?
And then negative.
Well, that's what we use for inverse notation. But what did we do with those graphs to find inverses?
You just flip on this.
Switch the x and y. Okay, so now let's say we have this exponential function, y equals 2 to the x. So how would we find the inverse of that function? Switch the x and y. X equals 2 to the y. And now we need to solve for y, because when we find inverses, that's what we do. We switch our x and y, and we solve for y. But y is an exponent. So how do we solve for an exponent?
Plug in the other one.
Logarithm. Logarithm. So let's switch forms. This would be log. What is my base? 2. What is my answer part? X equals, what is my exponent? Y. Now I have solved for y. So if we start out with an exponential function, and we want to find its inverse, we switch the x and y and solve for y. Well, when we do that, we're solving for an exponent, and to solve for an exponent, you have to use a logarithm. Okay? You tried 2 and 3, and I'm going to change number
Plus the
4.
inverse one?
Okay, so we switch the x and y, so we get x equals 3 to the y, and then we switch forms. Y equals log base 3 of x. You switch the x and y, x equals 5 to the y, and then switch forms. Y equals log base 5 of x. Okay, so let's look at the new number 4. I changed number 4 to y equals e to the x, so if y'all could change that on your notes. So we switch the x and y. We get x equals e to the y, and we solve for y by switching forms. Y equals log base e of x. Well, do we ever leave it log base e? No? How do we write log e? Natural log of x. Log natural. All right, any questions? Okay. We're going to start graphing these by using what we know of exponentials. Then we're going to let go of exponentials. We're going to say bye-bye to exponentials, and we're just going to concentrate on the logarithms. But the first 2 examples we do here is going to tie back into what we know about exponentials. Since I only make you do 3 points, let's identify 3 points that would be on this exponential graph. Y equals 2 to the x. That was our number 1 here. Y equals 2 to the x. So if I plugged in -1, let's just do a chart. If I plugged in -1, what would I get out for y? 1/2. If I plugged in 0, what would I get out for y? And if I plugged in 1, what would I get out for y? This is the parent graph. Y equals 2 to the x is the parent graph for an exponential in base 2. And normally we would start by graphing our horizontal asymptote and then plotting our points. And then drawing in our graph. I wonder if I can change the color this way. I don't think so. Nope. Okay, bye. So on this one, what is the domain of that function? From negative infinity to positive infinity. And what about the range?
Is it for parentheses, like parentheses 0 to positive infinity?
Good. And does it ever cross the x-axis? No. So would it ever have a 0?
No.
No, it doesn't cross the x-axis. All right. So now let's look at 3 points that would be contained on the graph of this. Well, we started out with this one, and log base 2 of x is just the inverse of this. So what can we do with all of these? Just switch them. So we've got 1/2, 1, 2, and -1, 0, 1. So when we graph that, we go over a half, down 1, 1, 0, and 2, 1. Oops. Now, does it look like it's a reflection over that y equals x? Pretty good. Pretty close. Okay, now let's look at, this is the y equals log base 2 of x, and this one was y equals 2 to the x. So this was our exponential that we've been studying. This is our new log. So the log is just a reflection over that y equals x, and the log functions are going to look like that. So instead of having a horizontal asymptote, what do you think these are going to have? So log's going to have a vertical asymptote, isn't it? We switch the x and y, we switch those horizontal asymptotes to vertical asymptotes. So this has a vertical asymptote at x equals 0. If we have switched our x and y, we've switched our input and output. That also means we've switched our domain and range. So the domain is from 0 to infinity, and the range is from negative infinity to positive infinity. Now, this one never crossed the x-axis, the exponential. But does this one cross the x-axis? Yes, it does. So we have zeros on this one. We have a 0 at 1, 0, don't we? You can clearly see that from the graph.
Wait, what is it?
0, that's, that doesn't look much better. Okay, y equals 3 to the x, and y equals log base 3 to the x on this graph here for number 8. you do? Good, good. All right. Now let's think about what we would do if we were not graphing the exponential at all. How could we graph one of these if we were not graphing the exponential part at all? Okay, so I'm erasing mine now, and I'm going to do a new problem. You just watch this, and we'll talk about it in just a second. So I'm going to use the same graph, but I'm going to do y equals log base 5 of x. What would I do to graph this without having to graph the exponential? So what we would do is first we would switch forms, because this is hard for me to do. So when I'm in log form and I don't know what to do, I can switch back to exponential. In exponential, what would this be? 5 to the y equals x, right? Well, when it's in this form, it's pretty easy to actually pick values for y and figure out what x should be. If I picked -1, 0, and 1 here for y, what's 5 to the -1? 1/5. What's 5 to the 0? 1. What's 5 to the first? 5. So when I look at a logarithm, instead of plugging in values for x and trying to figure out what y should be, it's easiest to plug in values for y, and then you just evaluate x. It's much easier. Okay. Since this one was not shifted right or left any, I can go ahead and draw in a vertical asymptote at 0. There's my vertical asymptote. And then it's not shifted up or down, so my points would all start from the origin. So if I think about this, this is over a fifth, down 1. Over a fifth, down 1 is pretty close. Over 1, up and down 0. And over 1, 2, 3, 4, 5, up 1. And then there are the 3 points I'll be looking for. And you draw in your graph. And then you could do the domain and the range and the zeros. Now, the ones we've done so far, the zeros are pretty clear. They're on the graph. This next one we do, we're going to have to solve to find our zeros. So if it wasn't real clear, to solve to find your zeros, a 0 means where does the function have a value of 0? Well, what in this equation represents the value of the function? The x or the y? The y. The y represents the value of the function. So what we would do is we would plug in 0 for y and then just switch forms. So we get the base raised to the exponent equals the answer. What is 5 to the 0? 1. What was the 0 on this graph? 1. Does that make sense? Okay, now let's do the next one together. Okay, so now we're going to graph when we have some translations. We're going to do all types of transformations with this. We're going to shift, like this one, translate. We're going to reflect, and we might do some stretching and compressing. Okay, when we look at this, in this equation, what's accomplished by the 1? What does the 1 do? Okay, shifts right 1 unit. What does the 3 do? What does the 3 do to the function? Shifts it up 3. Yeah, last period I left the F out. Yeah, it was a bad morning. But I worked out all the kinks last period, so y'all are getting a new and improved teaching experience. They were very mature about it. I don't even, they were either mature or nobody was paying attention to me, one or the other. But it worked out well. All right. So on this one, logarithms have vertical asymptotes. So just like when we were graphing the exponentials, and we started with our horizontal asymptote, on the logarithms, we're going to start by graphing our vertical asymptote. Bless you. All right, so our vertical asymptote is going to shift over right 1 unit. So there we go. Let's graph that first. Yeah, the quality of the copies are not so good this time. I'm not sure what's going on. And then this +3 is going to shift our starting point up to here. Now, I'm only going to show you graphing by moves for the logarithm because I feel they're the easiest. If you like to pick x values and plug it in and determine what your y values would be, you can do that. I just find that much more difficult. All right, so here we are. If I go ahead and take care of the shifts, all I have to graph from that shifted point is the parent graph, which is y equals log base 2 of x, which is 2 to the y equals x. And I told you it's easiest to pick your y values. So if you do -1, 0, and 1, that is the easiest way to do this. So what is y to the negative first? 1/2. What is y to the 0? And what is y to the first? 2 to the first. I kept saying 1. Thank you. All right, so from this shifted, translated point, we're going to go over 1/2 down 1, 1, 0, and over 2 up 1. And we have shifted our parent graph. All right, those shifts changed our domain. What is the domain now? 1 to infinity. Did the shifting affect the range? No. But the shifting did affect the zeros. So this is the equation I started with. Y equals log base 2 of x minus 1 plus 3. And we want to know when this function has a value of 0. And now we're supposed to solve. But the problem is I'm not quite in log form. I've got this extra 3 right here. What could I do to get rid of this extra 3? Subtract it. So now I have -3 equals log base 2 of x minus 1. Now I'm good. I've got an exponent part, I've got a base part, I've got an answer part, and that means nothing to me. So when I get tricked, when I get stumped when it comes to logarithms, I always switch forms. So, switch forms. Let's go to exponential. What is my base? 2. What is my exponent? -3. What is my answer part? X minus 1. Well, this is just 1/8 equals x minus 1. So 1 and 1/8 equals x. That is my 0. That is where the function has a value of 0. So the 0 is 1 and 1/8. Okay, I will do one more with you, and then I'm going to let you just work on your own. But ask me questions as you go, okay?
Where is that sheet?
This sheet is on my, it should have been on the back. But somehow all the papers I sent to county office to get copied, I don't know if the big paper clip came off and they all fell on the floor and they picked a new order. But this should have been on the back. I don't know if I sent them wrong. That is a possibility. I've been goofing up a good bit here recently, so that could have happened. But they didn't get copied the way I
on the back of the other worksheet.
So let's look at number 11 together. Y equals ln of x plus 3, quantity plus 2. All right, so let's take care of those shifts, and then we can ignore this and this. Where is that vertical asymptote moving to?
-3.
-3. Where, now on this vertical asymptote, where do I put the starting point for my moves to originate from? Up 2. So now that I took care of all that, all I have to think about is the parent for this graph, y equals ln of x. So if we're going to make that table where we plug in the -1, 0, and 1 for our y's, we've got to figure out what this is. Let's switch forms here. What's my base? E, and my exponent is y, and it equals x. So to get x, I have to do e to the y. So e to the -1. That's, e is 2.71828. So this is somewhere between 1/3 and 1/2. A little bit closer to 1/3 probably. What's e to the 0? 1. And what's e to the first?
2.7.
Yeah, we'll approximate that. It's 2.7. So if I go over about 1/3, I go down 1. 1, 0. And if I go over 2.7, I go up 1. And there are 3 points. What is the domain of this graph? -3 to infinity. Range? -infinity to +infinity. And zeros. We're going to have to do a little work on this one. We plug 0 in for y.
Just 1.
And then we got to move that 2 over to get it in log form. Whoops. And then we switch to exponential form. So what is the base?
E.
E. So e to the, what's the exponent?
-2.
-2 equals, what's the answer part?
X plus 3.
X plus 3. And then we move the 3 over, e to the -2 minus 3 equals x. And the only other thing I could do with this, instead of leaving it e to the -2, I could write it 1 over e squared. And that's it. That is my 0. That is the exact
But isn't it 0 just
0.
1?
Huh?
Isn't 0 just 1?
Where does it cross the x-axis? Right here
Oh.
is your 0. So, yeah.
Should you write it as an e squared?
I would accept it either way. Okay, now if we look at some of these, this one has a negative right here. What's that going to do to this graph if there were a negative? It's going to flip it. There's not a negative, but let's say there were a negative out in front here. All it would do is take this point up here, this point down here, and flip it. Does that make sense? Okay. What if there were, instead of a negative here, there were a negative inside here? What would that do?
Move it that way.
It would flip it over here, wouldn't it?
Oh, really?
Wait, 2.7
But
there.
wouldn't it move it also?
Yeah, if it's negative outside the equation, would it be
Make
negative?
3, make it 3 then also?
If it were this, it would switch it to the opposite, but I went ahead and factored out the negative. The negative always has to be factored out. I don't give you a whole lot that look like this.
No, but it would be minus 3 then, wouldn't it?
X minus 3.
Because then the negative would distribute, so
So it'd move it over to the positive.
negative x minus 3. Wouldn't it?
And in transformational form, if it's reflected here, it has to be factored out of that horizontal shift. So if I had given you one like this earlier, the only time I've really ever given you a negative with the x is when there's no horizontal shift. If there was a horizontal shift, it would have to look like that. This would be a shift left 1 and then reflected. The negative has to be factored out. If the negative isn't factored out, that's the first thing you have to do, is factor the negative out before you can look at the shift. That's left 2. And we haven't done a whole lot like that. All right, I would like you to work on the remaining graphs, and then these book problems are quick. It is just switching forms. So, give an exponential right log. I want you to ignore the directions on page 205, and I just want you to switch forms. That's all we're doing on those 16, just switching forms. That should take less than 2 minutes. So if you want to go ahead and do that and just do it at the bottom of your graph sheet or on the back of that graph sheet, that is totally fine.
So is this homework as well?
Yes, finish the graphs and then those quick problems out of it. But you have the rest of class, so you have